Hello, bright minds. Quick question. Have you ever tried standing in front of a mirror holding a candle flame and wondered where exactly is the image of that tiny flame hiding? Well, here's the catch. A point object, like that flame, doesn't just send light straight into your eyes. Oh no, it sprays rays in all directions like a firework. To find where its image forms, we don't need to chase every single ray. Two rays are enough. So, let's take two rays from the object O, one striking at point A on the mirror and the other at point B. We also draw normals at A and B, call it N1 and N2. These rays will reflect off, obeying a golden rule, angle of incidence equals angle of reflection. The stage is set for image formation. Now watch the reflection magic. The ray OA reflects as AC and OB reflects as BD. They spread apart, diverging in front of the mirror. If you're standing at point C or D, your eyes catch those rays. And here's the physics twist. At each reflection point, the law holds tight, angle I equals angle R, no exceptions, no holidays, no cheating. That's why mirrors are such reliable storytellers of geometry. So far, we've got two rays bouncing off, but they don't meet in front of the mirror. So how do we see an image? Patience, let's trace them backward. Let's pull out our imagination. Extend the reflected rays AC and BD backward into the mirror like dotted lines. Surprise, surprise, they meet at a point I behind the mirror. That's our image of O. But remember, those rays don't physically converge there. It's just an optical illusion cooked up by geometry. That's why the image is called virtual. So, if you ever wondered why you can't catch your bathroom reflection on a screen, it's because the rays never actually meet behind the mirror. The image is virtual, not real. Now, what does the human eye do in this story? When rays AC and BD enter your eye, your brain, being the wonderful detective it is, assumes they've traveled straight lines. It extends them backward and reports, aha. The object must be at point I behind the mirror. That's why the image appears at the same distance behind the mirror as the object is in front. And here's a fun fact, the image is erect, of the same size but laterally inverted. Ever noticed how the word left becomes TFL in a mirror? That's lateral inversion in action. Let's do a quick calculation. Suppose the object is 5 centimeters in front of the mirror. Where is the image? We use the rule for a plane mirror, image distance V equals minus object distance U, that is, V equals negative U. So, substitute U equals 5 centimeters. Then V equals minus 5 centimeters. That means the image is 5 centimeters behind the mirror. And what about the nature? Virtual, erect, same size, laterally inverted. Boom, one formula, full description of the image. So, let's wrap it up neatly. A point object in front of a plane mirror sends rays in all directions. Take two rays, apply the reflection laws, extend them backward, and you locate the image behind the mirror. Key takeaways: image is virtual, erect, and laterally inverted. Object distance equals image distance. And you can never catch this image on a screen, it lives only in the world of perception. So next time you wink at yourself in a mirror, remember, it's not the mirror copying you, it's just rays and geometry conspiring to make you look fabulous. See you in the next session where we'll dive deeper into the magic of light and its playful tricks.